Beneath our feet lies a silent world. The ground that supports every city, every road, every routine. And sometimes, that ground turns against us. In 2016, in Hakata, Fukuoka, Japan, a major road collapse shocked the nation. A tunnel construction zone deep below the city triggered a sudden cave-in above. In seconds, one of the busiest urban spaces was transformed into a crater. And yet, in just 1 week, Japan demonstrated something remarkable, not only emergency response, but the fusion of geotechnical engineering, construction management, and resilience. But the threat is not limited to construction zones. In Yashio, north of Tokyo, aging underground infrastructure quietly created the conditions for disaster. Corrosion advanced in darkness until the ground above could no longer hold. Invisible decay, difficult to predict, devastating when it finally appears. This is the new battlefield facing mature cities around the world. And now, the stage moves to Thailand, a nation of rapid growth, complex urban infrastructure, and some of the softest urban ground conditions in the world. Here too, the struggle beneath the surface is intensifying. In Thailand, what we are seeing is not a collection of isolated accidents. It is the emergence of a pattern. Across Bangkok and its surrounding areas, pavement collapse, sinkholes, and road subsidence are appearing again and again, revealing a growing instability beneath one of Southeast Asia's most dynamic urban environments. In 2024, the warning signs were already there. A major sinkhole opened on Bang Ngo Trap Road. At Kesa Komon Bridge, pavement failure followed a water pipe break. Near Sukhumvit 64, a road collapse trapped a truck. Different sites, different triggers, but the same underlying message: the subsurface systems supporting the city are under increasing strain. In 2025, the consequences became more visible and more serious. A large sinkhole appeared on Kangwatana Road. A dramatic collapse occurred in front of Vajira Hospital, directly affecting a sensitive urban zone. And on Charoen Krung Road, subsidence appeared again near critical utility infrastructure. These were no longer isolated inconveniences. They were urban disruptions with direct implications for safety, mobility, and city operations. In 2026, the pattern did not stop. Road collapse was reported on Charan Sanitwong Road at Phai Chai intersection. Road subsidence also appeared on Phetchaburi Road, one of Bangkok's most important corridors. What with timeline reveals is not only recurrence but escalation. The locations may differ, but the threat is the same: hidden instability beneath roads used by millions of people every day. These images are more than a record of accidents. They are evidence of a growing urban social issue in Thailand. Every collapse affects more than pavement. It disrupts traffic, threatens human life, damages utilities, delays emergency response, and weakens public confidence in the safety of the city itself. The question is no longer whether subsurface risk matters. The question is whether we can detect danger before the ground gives way. To protect the city above, we must first see beneath the surface. What we must protect is not only infrastructure, but the everyday life of the city. What we must build is not only stronger ground, but a more resilient future. Let us begin that discussion today.
The subsurface mapping technology simultaneously captures subsurface data with a GPR and surface data with a 360-degree camera. After both data are synchronized with GPS time, a unified database for efficient and high-precision infrastructure management is created. The subsurface mapping technology is composed of the GPR, camera, and GNSS, meaning that it can be installed with the same potential in different platforms such as hand-pushed carts, smaller or larger cars. This flexibility allows rapid deployment across diverse urban environments. Feature 1. 3D ground-penetrating radar system with multi-channel antenna arrays. Many antennas are aligned transversely to capture data in the additional dimension transversal to the antenna's travel direction. This allows for easy visualization of data in 3 dimensions, since the geometry of features can be seen in a horizontal slice. Cavities and buried pipes, which are difficult to differentiate in single-channel data, are easily identified. Feature 2. Mobile mapping system. The differential of the subsurface mapping technology in GPR survey is the addition of a mobile mapping system, or MMS. The system tracks reference points in the camera imagery to calculate the vehicle's accurate position and trajectory in a method called camera vector. The high-precision camera vector trajectory is then utilized to correct the GPR spatial information data, as well as to create an ortho image of the surveyed road. Feature 3. Unified terrestrial and subterrestrial data. This is what data visualized in the subsurface mapping technology viewer looks like. At the upper left, we have the GPR subsurface data, next to it the 360-degree camera imagery. At the bottom left, we can see the ortho image created with the camera imagery, and finally, we also have a localization map. The interesting thing about the viewer is that when checking an exact location in the GPR data shown by these blue cross lines, that same location is also displayed in the camera imagery by this blue arrow and in the ortho image by the blue circle. This ultimately allows for accurate and practical localization of subsurface features as seen from the surface, making it easy to understand where an underground feature is with the use of surface reference points. Feature 4. Exploration vehicle. With the subsurface mapping technology, we can utilize subsurface data as a fixed reference to spatially localize surface imagery previous to the disaster event. It is then possible to superpose the old imagery with the new data to know where buildings, roads, or land borders used to be, providing critical information for disaster response and urban reconstruction. Now, let us turn our attention to the practical application of this technology. Recently, we successfully deployed our system in Thailand, a region facing rapid urban development and complex challenges in underground infrastructure. We needed a solution that was non-destructive, highly accurate, and efficient. As you can see here, the system was mounted on local utility vehicles, scanning kilometers of urban roads seamlessly without causing any major traffic disruptions. Because the subsurface mapping technology easily adapts to different types of vehicles, we were able to quickly mobilize our team and begin large-scale data collection immediately. Between 2025 and 2026, we surveyed 823 kilometers of roads around Bangkok and discovered 606 potential cavities. By organizing these detected cavities onto a comprehensive map, we are currently conducting heat map research to visually identify and predict high-risk areas. This moves us from reactive response to proactive prevention, knowing where the next sinkhole might appear before it does. We are proud to share that our findings were recently reported at the NCCE31 conference. This landmark study represents the first-ever trend analysis of large-scale cavity investigations in Thailand. Based on a comprehensive 338-kilometer survey, we successfully identified distinct cavity formation trends across different urbanization zones and road lanes. Furthermore, through advanced physical tests and finite element analysis, we are developing a novel risk assessment framework tailored specifically for Bangkok's concrete pavements, moving beyond traditional asphalt-based standards. Furthermore, we are thrilled to announce the publication of the very first technical standard for underground cavity investigation in Thailand. This groundbreaking document was developed and published based on the successful outcomes of our joint research with Ehime University and King Mongkut's University of Technology Thonburi, or KMUTT. This standard will serve as a vital guideline for standardizing proactive road maintenance and preventing road collapses across the nation. We will continue to work in collaboration with universities in Thailand and Southeast Asia to address the challenge of promoting the GMS3 technology, which is the most effective solution for preventing cave-ins caused by underground cavities.